On the morning of November 27th, 3 separate observatories across 3 different continents experienced something they couldn't explain. It started just before dawn in Spain, where the Calar Alto Observatory had begun its usual morning tracking sweep of 3i Atlas's outbound trajectory. The skies were clear, the instruments were calibrated. The software log showed a lock on the object's predicted coordinates. Then, without warning, the imaging feed went black. There was no warning alert, no sensor error, just a sudden absence, like the frame had never existed. Less than 5 minutes later, halfway around the globe, a similar event occurred at the Thai National Observatory in Chiang Mai. The telescope's deep sky imaging unit registered a complete dropout in the same sector of sky. At first, technicians assumed a power fluctuation, but the power logs showed no dip. The temperature sensors were normal, the telescope had full mechanical function, and the object, 3i Atlas, was still locked in the tracking system. The lens hadn't drifted, the image had just disappeared. A third event followed in northern Norway, where the Andøya Space Centre had been observing the object under polar night conditions, some of the darkest, clearest skies on Earth. Their high-sensitivity optical array captured something different. Not blackness, but a brief blinding overexposure. The screen lit up in pure white static, only for 0.7 seconds, before returning to its normal field. But when the frame buffer was checked, there was nothing. The system had failed to log that moment. No frame ID, no timestamp, just a blank gap in the sequence. 3 observatories, 3 continents, 3 separate failure modes, but all aimed at the same coordinates, the outbound corridor of 3i Atlas, as it continued its trajectory away from the Sun after perihelion. At first these seemed like isolated glitches, but it was the timing that raised red flags. All 3 outages occurred within a 10-minute global window, centered around the same right ascension and declination, and what's more, their systems were entirely independent. Different software, different tracking stacks, even different optical wavelengths, yet all were disrupted while observing the same object. When internal teams reviewed the logs, another strange pattern emerged. Each observatory's archival image storage system had triggered an automatic backup failover, but not to local drives. The systems redirected image saves to off-site repositories that were either empty or inaccessible. No images, no error codes, and no restoration files. At the time, this was classified as a rare edge case failure, until someone at the Norwegian observatory cross-checked the packet logs and discovered something else. During the exact moment of the overexposure, the system's network output was redirected to an IP address range registered to the European Space Agency. No such transfer had been authorized, and yet the log showed a complete handshake protocol followed by a silent data offload and termination command. In Spain, a junior technician noticed that their auto-alignment protocol had quietly updated its tracking kernel just seconds before the blackout. The patch was time-stamped with an internal signature labelled NASA JPL Override Mode 3, but no such patch had been scheduled, and no one had requested outside control. Thailand's observatory reported something even stranger. Their time server logs, which typically sync with the National Atomic Clock, showed a 4-second rollback immediately following the blackout. It was as if the system had momentarily rewound, skipped a timestamp, and resumed recording. Put together, these 3 anomalies, disappearance, overexposure, and rollback, suggest not just a technical failure, but a coordinated blackout. A moment when something in the sky was seen, or about to be seen, that triggered a suppression protocol across separate systems. Whether human or not, that kind of global-level coordination doesn't happen by accident. It happens when someone, or something, doesn't want us to watch. At exactly 4:19 in the morning, the Calar Alto Observatory in southern Spain began imaging a very specific patch of sky. They had been tracking 3i Atlas since before perihelion, but now the object was entering a stretch of its outbound path that many believed could reveal its internal structure, if there was anything to reveal. The telescope's optics were locked, calibrated, and aligned perfectly. Atmospheric conditions were ideal. There were no clouds, no turbulence, nothing out of the ordinary. And then, as the system prepared to capture its most detailed frame of the night, the data vanished. The system didn't crash. The telescope didn't lose alignment. The log even confirmed that the image had been taken. But when the technician opened the storage folder, the frame simply wasn't there. The image, the one centered on 3i Atlas at its brightest, was gone. No file, no thumbnail, not even a name. At first, they thought it was a buffer error, maybe a temporary disk glitch, but every test came back clean. No memory failure, no overheating, no power interruption. The imaging software had executed its routine normally. It had written something, and then erased it. Even the backup system failed. The observatory has a low-resolution autosave feature, just in case of corruption. That too was blank, and that only happens if something tells the system not to record at all. The missing image had a label, frame 44107. It should have contained a direct close-up of 3i Atlas during its moment of highest solar backscatter, perfect conditions for reflecting internal structure, tail signatures, or surface anomalies. Scientists had waited weeks for this exact moment, and now it was gone, as if it had never existed. But the technician noticed something else. Right before the frame disappeared, the system received a silent redirect signal, something that had never happened before. A command buried deep in the log file, short and unexplained. It said the data had been rerouted through an external channel to a node known to be part of the Deep Space Network. That should not have been possible. Calar Alto isn't wired to NASA's backend. It's a publicly funded, university-managed observatory. It doesn't send data to deep space stations. And yet, the system behaved as if it had. A silent override. A handshake with an invisible command. One technician later described it this way. It didn't delete the image. It just handed it off, as if someone else was watching and they wanted to see it before we could. It gets stranger. The frames taken just before and just after the missing one were still intact. But they weren't normal. In both of them, at the very bottom corner, there was a faint curve of reflected light, like the start of a structure just entering the field of view. Too faint to interpret. But the angle and positioning suggested that whatever was reflecting sunlight had passed directly through center frame during the missing moment. If that frame had survived, it would have shown it clearly. But it didn't. One moment, one camera, one frame, gone without a trace, not corrupted, not blocked by weather, simply removed. And it happened during the exact 10-minute window when two other observatories, in Thailand and Norway, experienced completely different failures while targeting the same object. 3 systems, 3 countries, one silent moment. Whatever was in frame 44107, it was never meant to be seen. While Spain was still reeling from the disappearance of frame 44107, something equally strange was unfolding on the other side of the planet, at the Thai National Observatory, perched high in the mountains of Chiang Mai. Here the skies had been stable all night. No interference, no wind. The telescope's infrared tracking system had successfully locked onto 3i Atlas by 09:20 local time, aiming for a perfect cross-section of the object's tail region. This was one of the few locations on Earth where the timing, altitude, and geometry were just right to view the object from a lateral angle, capturing not just its brightness, but the spatial shape of its trailing material. But something happened the moment the system tried to save the second image in its tracking sequence. The screen flickered once, then again, then it looped. Instead of saving a new image, the telescope's software began replaying the previous frame, over and over again. A single still image, frame 1332, was displayed on repeat for nearly 6 full minutes. At first, no one noticed. The image looked fine, no static, no corruption. But it wasn't updating. The telescope was still tracking, still aligned, but the camera feed was no longer live. It had become a loop. The technician in charge thought the display software had frozen, but when he checked the raw directory, the system was still writing files. Frame 1333, 1334, 1335, each one marked with the correct timestamp. But when opened, they were all exact digital clones of frame 1332, bit for bit, pixel for pixel. It was as if the telescope kept taking the same image again and again, despite the object moving steadily across the sky. That should be impossible. Even the smallest movement of a celestial body creates minor changes in brightness, contrast, and position. But in this case, 6 minutes of data showed no change at all. It was as if the sky had frozen. At minute 7, the loop broke. The feed snapped back to real time. frame 1345 suddenly showed a sharp increase in contrast, followed by what looked like a radial flare at the centre of the object, bright enough to trigger the telescope's automatic dimming feature. The following frame, a 1346, was normal again, but the anomaly was gone. Only later did the team realise what had truly happened. The observatory's internal timing system had quietly rolled back by exactly 2.3 seconds during the loop. The logs confirmed it, a perfect reversal, then restart. There was no explanation, no internal command to do so, no reason for the system clock to shift. But it did, and it wasn't just the clock. The file access history for that 6-minute window had also been locked. The observatory's Linux-based operating system reported a permissions change that no one initiated, one that redirected write access to a temporary partition that disappeared after the session ended. When forensic specialists reviewed the session, they discovered something unsettling. The repeating images hadn't come from a frozen camera sensor. They had been intentionally regenerated from a single frame, written into the storage directory multiple times with artificially generated timestamps. In other words, the camera didn't freeze. Something replaced the real frames with a loop of a safe one, and it did so while maintaining the illusion that everything was functioning normally. The final detail was buried deep in the network logs. During the exact 6-minute loop, the observatory's upload bandwidth spiked, transmitting over 4.7 gigabytes of data to an off-site server listed under a generic academic exchange protocol. But that server had no name, just an IP address, and a country code, US. Thailand didn't lose a frame. It was fed the same one, on repeat, until the moment had passed. Which begs the question, what was the camera not allowed to see? Of the 3 observatories that experienced anomalies on the morning of November 27th, none had clearer skies, or darker ones, than the Andøya Space Centre in northern Norway. Located above the Arctic Circle, Andøya operates in near-total darkness during this time of year. With no sunlight for weeks and little atmospheric moisture, it offers an unusually clean window into deep space. On this morning, that clarity would prove both a gift and a curse. The team had calibrated its instruments just after 3 a.m. local time. Their target, 3I Atlas, now moving further from the sun but still trailing fragments of what scientists believed might be volatile gas jets, residual coma structures, or perhaps something stranger. At 03:27:44, the telescope snapped a routine frame. Clean, centered, nominal brightness. The next was scheduled for just a few seconds later, part of a rapid exposure sequence designed to capture any fast-changing activity around the object. But what came through next wasn't a normal image. It was white, not overexposed, not fuzzy, pure white. An intense, perfectly saturated burst filled the entire sensor. Every pixel hit maximum brightness. It wasn't noise, it wasn't solar interference, and it wasn't a glitch. The telescope is designed to detect overexposure and compensate by automatically adjusting exposure time, but it never had a chance. The whiteout lasted just 0.7 seconds, then it stopped. The frame after that showed 3I Atlas again, dimmer than before but intact. No system failure, no signs of internal reflection or lens flare, just one blinding moment, then silence. And yet, the real mystery came not from the flash itself but from what followed. The Andøya data server, which saves all raw frames to both local and cloud storage, showed a blank entry where the flash should have been. Frame 8874 was listed, but when opened, it returned an error. Corrupted file header. The frame could not be previewed, copied or moved, but it could be counted, and that's what caught the team's attention. The metadata of frame 8874 indicated a file size of exactly 0 bytes. It hadn't failed to record. It had recorded nothing. Even more suspicious, a network log showed that during the same 0.7 second window, the system transmitted a high-volume data packet to an unlisted subnet, far outside Andøya's usual outbound range. The transfer took only milliseconds. It was logged, time-stamped, and immediately followed by a temporary shutdown of the observatory's internal archive viewer. In effect, the system saw something. It sent it elsewhere, and then locked the door behind it. An hour later, the archive viewer came back online, but frame 8874 remained blank. The technician on duty filed a report and moved on. until, reviewing the frames before and after the flash, he spotted something unusual. In frame 88873, a small but clearly defined arc of light appears in the lower left quadrant, just emerging from the edge of the image. It's not a star, it's curved, metallic in texture, sharper than any known fragment of cometary material. The object appears to glint, not glow, suggesting it reflected sunlight rather than emitted its own. Then, in frame 8875, it's gone. Whatever crossed the telescope's view during the whiteout was fast, deliberate, and visible only for a single fraction of a second, precisely when the frame vanished. Some might argue it was a cosmic ray or electrical discharge. But cosmic rays don't trigger network transfers, and they don't leave geometric shapes. Andoya's team, known for their discretion, published nothing. No anomaly alerts, no press releases, only a quiet internal note labelled Flash Event 8874 under review. But in the private Slack channel used by the technicians, one comment stood out. That wasn't a failure, that was someone pulling the curtain shut. After the events of November 27th, researchers began comparing logs from the 3 observatories affected that morning: Spain, Thailand, and Norway. Initially, the anomalies seemed disconnected. One had a missing frame, one experienced a looping replay, and the third was hit by a blinding whiteout. Different systems, different continents, different failure modes. But then, one analyst, working independently from a university in the Netherlands, made a quiet discovery that changed everything. Despite the geographic separation, and despite the varying timing of each event based on local time zones, all 3 observatories had been pointed at 3i Atlas from roughly the same spatial orientation. They were seeing the object from different parts of Earth, yes, but from space. The angular offset between each view was minimal, almost non-existent. Using right ascension, declination, and telescope azimuth logs, the analyst reconstructed the relative geometry of each observatory's line of sight at the exact moment the anomalies occurred. The results were shocking. Each camera had been targeting 3i Atlas from an angle of within 14 degrees of one another. That is vanishingly small. Equivalent to watching an object the size of a tennis ball from over 100 kilometers away and seeing it from the same perspective. But what's more, each incident occurred as the object passed through the same angular corridor in space. Not just the same general region, the exact same slice of sky, like a plane flying through a searchlight beam, or a sensor crossing a tripwire. That's when a second pattern emerged. Each anomaly happened just as the object rotated, or more accurately revealed, a specific surface angle toward Earth. By syncing timecodes from the Spain, Thailand, and Norway sessions, and correcting for Earth's rotation and location, researchers saw that the object's orientation had matched nearly perfectly in all 3 captures: 3 different cameras, 3 different instruments, and all of them were positioned to see the same face of 3i Atlas. This couldn't be explained by coincidence alone. If the object were truly tumbling randomly, there would be natural differences in how each observatory recorded its structure. Slight changes in tail direction, thermal variation across different hemispheres. But in this case, the brightness gradients, flare angles, and alignment of surface shadows were identical across all 3 sites, up until the moment something went wrong, and it was always that same angle that triggered the failure. In the Spain frame that never saved, the logs showed the telescope had just begun adjusting contrast to compensate for a reflective spike, the kind seen when sunlight bounces off a flat or polished surface. In Thailand, the looping started when the object entered that same contrast window, and ended when it rotated away. And in Norway, the blinding flash occurred the moment the object rotated to full exposure along that surface vector, as if a beam of light had ricocheted directly into the sensor. From that angle, 3i Atlas wasn't just bright, it was structured. Some theorize that this face of the object contains a surface distinct from the rest, smoother, flatter, or possibly reflective, in ways that defy ordinary cometary material. A geometry that only becomes visible when viewed from a very specific vector, and every time Earth aligned with that vector, something intervened. Whether the blackout events were triggered automatically by detection or deliberately by design remains unknown. But what's now beyond question is this: the failures weren't random. They were synchronized by angle, not by country, not by telescope, not by chance. 3 observatories, 3 moments of contact, 1 forbidden view, and all of them tried to look at the same face of an object that, maybe, wasn't meant to show its face at all. When astronomers talk about angles, they're not speaking in metaphors. In observational astronomy, an angle isn't just a direction, it's a permission slip. It defines what you're allowed to see, what's hidden behind curvature, and what geometry reveals itself under light. And on November 27th, the angle that triggered global anomalies in Spain, Thailand, and Norway was not just any orientation, it was the orientation, the one that exposed the truth about 3i Atlas. To understand why this angle matters, you have to consider the object's shape. From the beginning, 3i Atlas defied classification. It wasn't symmetrical like a standard comet, it didn't tumble like a rock. Instead, every rotation, every photometric reading hinted at deliberate asymmetry. Certain sides emitted infrared differently, certain faces reflected sunlight more sharply. And one specific region, the one exposed during the anomalies, behaved like a mirror. When the three observatories locked onto that exact angle, they weren't just looking at the object, they were looking into it. Surface reflections at that moment did not behave like dust or gas, they aligned sharply. The light spike in Norway didn't diffuse outward, it rebounded. That suggests the presence of a flat, possibly engineered plane, capable of high reflectivity and coherent scatter, and most critically it only appears from one angle. Now here's where things escalate. Shortly before the blackout events, a narrowband radio telescope in Sardinia detected a brief frequency distortion, a bend in the L-band, the same region used for deep space communication. It lasted under 300 milliseconds, but when traced back, it aligned perfectly with the moment all three observatories were facing the object at the same angle. It's as if something responded. Not continuously, not automatically, but conditionally, triggered only when a very specific visual threshold was crossed. A field of view activation, in effect. In covert surveillance technology, this would be called a line-of-sight protocol. Systems that only respond, transmit, or engage when being observed from a specific geometry. This kind of targeting is not new in engineering, but in astrophysics it's unprecedented. Because the implication is simple. 3i Atlas may have reactive geometry, a surface orientation that changes behavior when observed from a precise vector. That behavior could include increased reflection, electronic interference, or even defensive countermeasures, such as the imagery directions we saw in Spain and Thailand. Think about that for a moment. An object drifting through our solar system, exhibiting no consistent radio output, no clear rotation, and no artificial emissions, until Earth happens to view one particular slice of it. And then everything breaks. There's more. When plotted in a celestial coordinate grid, that angle intersects with the orbital inclination of Earth, meaning it becomes visible to us only during very narrow time windows, when Earth's position and spin happen to align just right. These windows are rare and short. The one on November 27th lasted just 11 minutes, and within that sliver of time, three observatories, without coordination, looked directly into that angle. All three experienced failure. That tells us the angle isn't just optical, it's functional, it has consequences. Some scientists have already begun calling it the silent sector, the slice of 3i Atlas that resists observation, reroutes data, and possibly modulates its interaction with Earth based on whether or not it's being seen. Why would any natural object care about being seen? It wouldn't. Which is why this angle matters. It isn't about illumination, it's about exposure, not to sunlight, but to us. And something out there clearly doesn't want that exposure to last more than a few seconds. In the hours following the November 27th anomalies, all three observatories began running internal diagnostics. At first, the assumption was innocent, perhaps a temporary buffer failure or a far-right collision. But what they found instead sent quiet ripples through back-end engineering teams. Not because of what they saw, but because of what they weren't supposed to see. Each observatory had recorded an override event, and all three happened in different ways. At Calar Alto in Spain, the override took the form of a line in the system log, a redirection protocol. But it wasn't labelled as a crash. It didn't throw an error. The system simply acknowledged a background command that told it to reroute one image frame, frame 44107, through an external channel, with no internal confirmation. In Thailand it was subtler. The log didn't mention any override. But forensic analysis of the session directory revealed that access permissions on the looped frames had changed, not after the anomaly but milliseconds before. The ownership tag of the file switched from a local user to an unlisted system-level process, which temporarily locked the directory. Then, as if nothing had happened, the permissions reverted. 6 minutes of activity, surgically removed from human hands, and then in Norway, the strangest signal of all. Not a log entry, but a network flag, a diagnostic heartbeat usually used to monitor internal latency. At exactly 3.744, the moment of the whiteout, the system issued a spontaneous packet redirect. Not because it was told to, but because a software layer above the operator level issued a remote reallocation of bandwidth. The data pipeline had been hijacked silently and then returned to normal. In every case, the override left behind almost no trace, no warnings, no confirmation boxes, no crash reports, just a clean, low-level adjustment in the system's operating logic. As if a shadow layer of software had temporarily taken control, executed a small command, and stepped back without leaving fingerprints. But here's where it becomes impossible to ignore. All 3 override events happened within the same 21-second global window. 3 observatories, 3 override commands, 3 different languages, systems and architectures, all triggered at the same moment, aimed at the same object. The term override implies control, a higher priority system stepping in to supersede local instructions. But the engineers at the Spanish observatory made a chilling observation. They couldn't find where the override came from. There were no calls from external IPs, no signs of packet injection, no user authentication events. Whatever initiated the command came from inside the operating environment, but not from any known process. It was as if the system had been waiting for a condition to be met, and when it was, the logic executed instantly. This raised an even more unsettling question. What if the override wasn't triggered externally at all? What if it came from the object? Every observatory was connected to global ephemeris servers, data centers constantly updating the orbital path of 3i Atlas, using real-time tracking solutions. These systems use automated updates, often syncing with other observatories via satellite relays. And those relays are two-way, which means, under the right conditions, an outbound object, passing through the right vector, using enough energy or reflective geometry, could technically insert a signal into the return stream. It wouldn't need to hack anything, just emit structured electromagnetic noise that resembles an update, not a transmission, a command disguise. If 3i Atlas knew when it was being seen, and from where, it could potentially send conditional triggers that activate only when that observation geometry is met. We're not saying it's intelligent, but the override didn't come from us, and if it wasn't us, then something else decided those images didn't belong in our archives. While the optical anomalies on November 27th drew most of the attention, a quieter thread was unravelling beneath the visible spectrum, one that began before the missing images, before the flash, even before the override events. It started with heat. At 03:12 UTC, exactly 17 minutes before the visual blackouts were triggered, a thermal imaging unit in Granada, Spain, registered something unusual. This wasn't at the main Calar Alto Observatory, but a smaller auxiliary station outfitted with mid-infrared sensors tuned specifically for cometary surface analysis. The goal was to detect subtle shifts in surface temperature as 3i Atlas rotated, clues to sublimation, surface cracking, or dust jet activity. What they captured was neither subtle nor gradual. Instead of a steady thermal profile as expected, the camera recorded a sharp drop in surface temperature, limited to a narrow band on the object's leading edge, roughly corresponding to the same region that would later cause the visual systems to fail. This drop wasn't minor. It was abrupt, a 15 Kelvin decrease in under 90 seconds, and entirely isolated. The rest of the object's temperature remained constant. Even stranger, the cold zone retained a distinct geometric outline, not fuzzy, not rounded like a shadow. It was linear, straight, as if a panel or boundary had rotated into view. At first, the technicians suspected a sensor drift. They ran diagnostics. Everything checked out. The cold patch wasn't an error. It was real, and it was growing colder in perfect sync with the object's position shift, until the moment it rotated out of view, and the anomaly vanished entirely. Roughly 12 minutes later, a second thermal camera, this time from the Thai National Observatory, picked up a mirror event. As 3i Atlas moved into a new observational window, the same region on its surface began emitting an ultra-narrowband thermal spike, peaking briefly at 285 Kelvin, higher than any part of the object had shown before. But the spike lasted just 3 seconds before dropping back to baseline. These two readings, one cold, one hot, were aimed at the same surface feature, but observed from opposite sides of the planet hours apart. And the timing matched exactly with the rotation model of the object's axis. What this suggests is that 3i Atlas possesses a reactive surface region capable of regulating or manipulating its own thermal emission depending on observer geometry. But here's what truly caught the attention of infrared researchers. The cold region in Spain was non-radiative. It didn't just get cooler. It stopped emitting entirely in the 10-micron band. That shouldn't be possible. Even the coldest surfaces still emit some thermal signature unless they're actively blocked, covered, or made from non-black body materials. In other words, the cold zone wasn't just cooling, it was shielded. And the hotspot in Thailand? It showed signs of anisotropic emission, where the heat radiated more strongly in one direction than another, as if it were being channeled, not just released. That behavior is extremely uncommon in nature, especially for a tumbling interstellar object without any internal regulation mechanisms. To some, this pointed toward internal structure. Not necessarily artificial, but compartmentalized, layered, with varying emissivity zones across the surface. But another group began asking a more radical question. What if this wasn't internal at all? What if the temperature shifts were triggered by our observation itself? If certain surface regions on 3i Atlas respond to specific electromagnetic signatures, like laser ranging or even passive detection in infrared bands, it's possible the object is reacting, not because it's intelligent, but because it's designed to hide when it knows it's being watched. This would explain why the cold zone only appeared when viewed from a precise vector, why the heat spike happened during the exact window of direct observation, and why both events preceded the visual anomalies by mere minutes. Because before the cameras were blocked, the heat signatures told the story first. 3i Atlas wasn't just turning, it was changing. At first glance, the events of November 27th appeared chaotic. 3 observatories across the planet, Spain, Thailand, and Norway, each experienced different types of failure, a missing frame, a frozen loop, and a blinding flash. Different systems, different triggers, different symptoms. But behind that chaos, buried deep in the technical metadata of each event, was a quiet thread tying them all together, the time codes. It was a junior systems analyst at the University of Geneva who first noticed it. While comparing public logs from the Cala Alto and Andoya observatories, he realized that both anomalies, despite occurring in vastly different local time zones, lined up exactly when converted to Coordinated Universal Time, UTC, to the second. Then he brought in data from Thailand. Same result. The missing frame in Spain, the optical loop in Thailand, and the whiteout in Norway had all occurred within a 21.3 second window, measured against atomic time servers. That would have been remarkable on its own. But the real discovery came next. When he overlaid the time codes with 3i Atlas's rotation model, something clicked. That 21-second global window aligned with a very specific orientation of the object, the same reflective angle that previous chapters described as the trigger vector. But this time, he went deeper. He pulled logs from every observatory that had tracked 3i Atlas in the 7 days prior. Most of them hadn't experienced failure, but many had noted minor issues: visual instability, time drift, micro glitches in file handling. And every single one of those minor disturbances, they also occurred at intervals tied to multiples of that same 21.3 second window. That is, 21.3, 42.6, 63.9, up to over 300 seconds of phase spacing. The interval repeated, again and again, whether it caused major disruption or only left behind tiny clues. It wasn't random, it was a pattern. What emerged was a clear harmonic structure, something that physicists call a temporal resonance. The object's orientation was syncing up with Earth's position, creating precise moments of alignment, windows in which something changed in the way 3i Atlas interacted with sensors. At first, researchers thought this might be observational bias, a coincidence of orbital timing. But then the Geneva team discovered something they weren't prepared for. In the system clocks themselves, independent of any telescope, micro-adjustments were being recorded at exactly those intervals. Internal logs on closed-loop observatory networks, with no public internet exposure, showed millisecond-level rollbacks or jumps in their atomic time calibration at the 21.3-second marks. This was deeply unsettling, because it suggested that the interference wasn't just optical, it was temporal. Now let's be clear, no one is claiming time travel. But modern observatories rely on high-precision internal clocks to sync multiple systems: optics, thermals, image buffers, and storage. If any of those clocks experience even a minor disturbance, the result can be misaligned data, frame skips, or corrupted timestamps. That's exactly what was happening, and only when the object faced a certain direction. It was as if the rotation of 3i Atlas was modulating a timed pulse, a signature of activity not just through space, but across timekeeping systems. The modulation didn't seem to carry data. It wasn't a message, but it was coherent, regular, repeating, and tied directly to object geometry. Some compared it to a heartbeat, not of a living organism, but of a system. A rotation-linked emission that interacted with external sensors, not by transmitting energy, but by subtly distorting how they track time. One observatory labelled it simply T-pattern echo, and once it was discovered, it started appearing everywhere. Systems began finding the same timestamp resonance embedded in old logs, weeks prior, unnoticed until now. Even faint oscillations in archived spectrograms aligned with the same 21.3-second beat. It wasn't loud, but it was there, persistent, predictable. Which leads to the deeper question. If an object can affect how time is measured, not universally but locally per observer, what else might it be modulating right under our instruments? The failures were loud. But the pattern in the time codes? That was the real signal. In the aftermath of the November 27th blackouts, a small subset of researchers began asking an unrelated question, or at least what seemed unrelated at first. Why did the angular position of the anomalies look familiar? That question was posed by Dr. Alexei Håkansson, an astrometry specialist based in Stockholm, who had spent most of his career studying signal alignment patterns in deep space telemetry. What caught his attention wasn't the blackout itself, but the celestial coordinates of 3i Atlas at the moment all three observatories experienced disruption. When plotted, the object was located along a declination line near a 27.5 degrees, with a right ascension that crossed a very narrow belt of sky used decades earlier for deep space listening experiments. Håkansson pulled historical logs from Ohio State University's Big Ear radio telescope, the same instrument that, on August 15, 1977, recorded one of the most famous unexplained signals in scientific history. It was known as the WOW signal. Lasting only 72 seconds, the WOW signal was a sudden, high-intensity narrowband burst that stood out so clearly against background noise that the astronomer Jerry Eamon famously circled it in red ink and wrote "WOW" in the margin. It was never heard again until now. When Dr. Håkansson overlaid the November 27th blackout geometry with the historical beam coordinates of the WOW signal, he found something astonishing. The object's orientation, and the Earth's position relative to it, matched within 0.7 degrees of the declination where the WOW signal originated. Not approximately. Precisely enough that if the Big Ear telescope was still operational and facing that vector, it would have been pointed directly at 3i Atlas in its current path. At first, skeptics dismissed this as coincidence. The sky's vast but finite, and overlaps can happen. But Håkansson went further. He analysed the time structure of the WOW signal, its frequency rise, peak duration and fall-off, and found an unexpected correlation. The 21.3-second temporal resonance discovered in the November 27th anomalies, it mapped onto the three-segment rise-plateau-fall of the WOW signal's intensity curve. In fact, the timing of the blackout alignment matched the middle plateau segment of the original WOW detection almost exactly. What does that mean? Some theorists suggest that the WOW signal was never a transmission in the traditional sense. It may not have been a message at all. Instead, it may have been a structured event, one that occurred when an object like 3i Atlas aligned with Earth at a precise angular vector. A spike. A moment of surface interaction, not communication. If that's true, then the events of November 27 weren't just visual failures, they were repeats. Recurrences of a geometric condition that had been met only once before, in 1977, when the Earth, the sky, and something beyond the solar system lined up in a very specific way. The blackout wasn't noise, it was the same silence. The radio spectrum logs from Andoya Observatory on the night of the flash also add weight to this idea. Though no strong transmission was recorded, a narrowband static smear appeared exactly at 1420-356 MHz, just slightly above the hydrogen line frequency, and identical to the range in which the WOW signal was detected. That number had puzzled scientists for decades. But if 3i Atlas isn't transmitting, if it's simply reacting whenever Earth looks from a certain direction, then the WOW signal and the blackouts may share the same root cause. A reflective event, not a communicative one. One driven by geometry, timing, and surface state. Dr. Håkansson has since released a quiet paper proposing that 3i Atlas may not be the first object to produce such an alignment, but it may be the first to loop back through Earth's line of sight twice within a single generation, a cycle, a return, and in that return the same coordinates produce the same result. The last time we heard it. This time, we watched it disappear. The European Space Agency is not known for drama. Unlike NASA, which often finds itself in the spotlight of political tension and public spectacle, ESA prefers quiet precision. Its operations are deliberate, its announcements carefully worded. So when an internal memo surfaced just 2 days after the November 27th blackout, quietly distributed to personnel inside ESTEC, ESA's primary technology centre in the Netherlands, it didn't scream, it whispered. But what it said was enough to shift the mood inside the agency from curiosity to containment. The memo, which has not been formally acknowledged by ESA but was confirmed through multiple independent sources, included a directive regarding 3i Atlas telemetry access. It stated that all collaborative data-sharing portals connected to external research groups were to be temporarily paused, effective immediately. No justification, no projected reactivation timeline, just a hard pause. To most scientists inside the agency, this was baffling. ESA doesn't cut off data pipelines unless there's risk, either to their instruments, to national security interests, or to ongoing private contracts. But this object, this visitor, was supposed to be open access. It had passed through international telescopes. The public had been tracking it in real time. There had been no prior reason to restrict anything. Until November 27th. That's when internal teams began cross-referencing sensor inconsistencies, particularly from the ESCAT radar facility in Tromsø, Norway, which had coincidentally experienced an unexpected power flux during the exact window of the Arctic flash. Though publicly dismissed as a calibration issue, internal emails revealed something stranger. ESCAT's ionospheric radar had picked up a coherent vertical signature just minutes before the optical saturation occurred. It wasn't natural. Interference, it had structure. According to one source close to the analysis, the radar return showed a localized ionization column in the upper atmosphere, consistent with a high-frequency reflection or incoming beam convergence. It was brief, less than 8 seconds. But it came from the exact region of sky where 3i Atlas had just passed overhead. This, reportedly, is what triggered the memo. ESA's leadership realized that what was unfolding had moved beyond passive observation. The object, or the way it was interacting with Earth, had caused physical effects detectable at ground level, and the European instruments had captured it first. Behind closed doors, a new task force was assembled. Not public-facing, not officially named, just a technical work group buried inside the Signal Coordination Office, tasked with reanalyzing historical 3i Atlas data through a new lens, one that looked for coherence, repetition, and shielding artifacts. Because the quiet question, now circulating in internal chat logs and hallway conversations, was no longer just, what is it? It had become, does it know we're watching? ESA's legal department also got involved. The language in international sharing agreements was re-evaluated. Export-controlled technologies, usually reserved for military-grade assets, were reviewed for their overlap with certain types of space-based emissions. There was even brief communication with the European Commission's Directorate General for Defence Industry and Space. That kind of movement doesn't happen unless someone believes the implications go beyond science, and yet no press release, no briefing, no leak to Reuters or ESA TV. The public-facing channels carried on with their usual cadence: satellite updates, climate tracking, solar flare maps. But behind the glass doors of ESTEC, every conversation about 3i Atlas became invitation only. One ESA engineer, speaking off record, said it best: "We've seen strange things before: cometary breakups, tidal anomalies, even false positive radar shadows. But nothing like this. This wasn't a discovery. It was a reaction. Ours." In other words, something about the November 27th alignment crossed a threshold, not because it gave us new data, but because it withdrew access the moment we tried to look too closely. And when an agency like ESA goes quiet, it's not because they have no answers, it's because the answers they do have don't belong in the open just yet. Among the 3 major observatories that experienced disruptions on the morning of November 27th, the Andøya Space Center in northern Norway initially had the clearest footage of 3i Atlas, until it disappeared. What makes this strange isn't just that Norway had the best vantage point, it's how rapidly their data became inaccessible. Andøya's advanced optical tracking system, nicknamed Polaris, is one of the few systems in Europe designed for high-contrast imaging under low solar conditions, optimized for near-Arctic winter skies. With no sunlight interfering and ideal atmospheric clarity that morning, Polaris began its scheduled pass of 3i Atlas at 0324 UTC, just 3 minutes before the visual blackout occurred across all 3 countries. According to internal logs later leaked from the Andøya facility, the system had already captured 8 consecutive full-resolution frames of the object, each one at 2.3-second intervals, with precision-aligned star background grids. These frames showed 3i Atlas in startling detail: crisp coma boundaries, a visible forward dust arc, and, most unexpectedly, a consistent reflective anomaly on the lower hemisphere of the object. That anomaly was unlike anything previously recorded by telescopes in Spain or Thailand. It resembled a partial ring, almost like a crescent reflection, rotating slowly as the object advanced, and then frame 9 never arrived. Polaris issued a camera read error at 3:24.19, the same moment that Thailand's optical systems entered their now infamous loopback state. Norway's system didn't freeze or loop, it simply stopped recording. The camera remained online, but the data buffer cleared itself. A full diagnostic sweep was triggered automatically by the observatory's AI management system. No fault was found, no overheating, no memory overflow, just silence. By the time the diagnostic finished, the object had rotated out of view. Technicians immediately tried to retrieve the 8 previously captured frames, but what they found was chilling. The primary archive folder was intact, but the image data inside had been replaced, not deleted. Overwritten with blank headers and 0-byte files, all labelled with correct timestamps, but no payload. Even more bizarrely, the system logs showed no user interaction. No one had accessed the machine physically or remotely. It was as if the recording module itself had decided to purge the most valuable images it had ever captured, without warning, without trace, and without a single mechanical fault. An independent backup server, located off-site and usually immune to internal file loss, hadn't even received the transfer. The relay stream had paused for exactly 4.8 seconds during the event, just long enough to skip the data block containing frames 6 through 9. Some initially blamed software corruption, but Polaris uses a redundant triple-layer write system designed specifically to prevent this kind of loss, even under physical duress. It had never failed in over 300 observation runs, so why did it fail now? There's a theory among the Andøya tech staff, unofficial, whispered, but consistent. They believe that 3i Atlas didn't just cause the disruption. They believe it reacted to the quality of the imaging. Polaris had the highest resolution, deepest thermal contrast, and best atmospheric alignment of all 3 observatories. It may have crossed an invisible line, observing the object too clearly, from too direct an angle. If the object contains surface materials or embedded logic systems capable of detecting the method or quality of observation, then it's possible Andøya's view triggered a response, a self-protective mechanism that interfered locally with the observatory's internal memory buffer. This wasn't a signal jam, it was a surgical erasure. Only the clearest data, captured at the most vulnerable angle, was targeted, and once removed, nothing else failed. Polaris continued operating as if nothing had happened. Except something had. 8 frames, a visible anomaly, the clearest glimpse we had of something not behaving like a natural comet. All of it gone. Norway saw the most, which is why we now have the least. Long after the anomalies of November 27th were initially dismissed as isolated technical failures, a single detail pulled the global scientific community back into focus. A light, small, faint, and consistent, that appeared in all 3 observatory frames, moments before the blackout. It wasn't a flare, it wasn't a reflection, it wasn't even centered on 3i Atlas itself, but it was there, tucked into the periphery of each disrupted image sequence from Spain, Thailand, and Norway. It first came to light, not publicly, but in closed researcher groups, when a postgraduate astrophysics student in Madrid was analysing the last uncorrupted frame from Calar Alto's session. In the top right quadrant of the image, near the limb of the starfield background, she spotted a pinpoint luminosity that hadn't been there in the prior frame. It held no motion blur, no cometary streaking, no atmospheric distortion. It was a perfect sphere of white, standing still against the sky. Curious, she cross-referenced the frame with star catalogues. No match. Then she corrected for time and rotational perspective, and found that in the Thailand frame loop the same light appeared, just 0.02 degrees lower on the z-axis. Again, unmoving. Again, not catalogued. It wasn't until the leaked backup logs from Andoya surfaced, specifically a partial reconstruction of frame 8, recovered using quantum pixel state analysis, that the confirmation came. The same light source was present in the Arctic footage as well. 3 observatories, 3 angles, 1 fixed point of light. This immediately eliminated random sensor flares or environmental interference. If anything, the triangulation created an opportunity. By mapping the parallax shift between each observatory's image, Spain to Thailand, Thailand to Norway, the light's approximate location in 3-dimensional space could be resolved. The result was alarming. The light source wasn't background, it wasn't in deep space, nor was it near 3i Atlas. It was between Earth and the object, closer than expected, floating somewhere in the mid-orbital region just outside geosynchronous satellite range, a blind spot in most global imaging systems, and it wasn't drifting. Further, analysis suggested that it held its position relative to Earth's horizon, not to 3i Atlas. That is, as the object moved and the Earth rotated, the light adjusted just enough to remain stationary to us, a behaviour uncharacteristic of any natural body. So what was it? Some speculated it was a probe, an observational unit, shadowing 3i Atlas from a distance, but only visible under extreme optical alignment. Others proposed a more grounded idea, a gravitational lensing artifact caused by a dense cluster of particles passing through a focal line, but that would require mass far greater than anything currently known near that region. The light was not bright in the conventional sense. In terms of magnitude, it barely registered above the detection threshold, but its spectral signature was unique. Preliminary spectral matching revealed a flat, almost sterile light profile, lacking the usual thermal emissions of stars, satellites, or debris reflection. It didn't spike in the infrared, nor did it echo any known artificial satellite signals. Even stranger, when researchers attempted to simulate the frames using reconstruction models, the light wouldn't resolve. Ray tracing techniques that correctly rebuilt the surrounding stars and comet features consistently failed to reproduce the light source unless it was manually placed, almost as if it didn't conform to the optical geometry of the rest of the image. Which leads to a sobering possibility. The light wasn't part of the scene, it was overlaying it, as if introduced at a post-capture level, bypassing natural light physics entirely. Whether this implies interference, projection, or some form of observational manipulation remains unknown. But what is clear is this. Right before the systems went down, right before the tail changed, the rotation pivoted and the files vanished. Something else was already there, watching, maybe, waiting, possibly, but unmistakably present, and only seen by those who looked, just before they couldn't anymore. Of all the anomalies observed during the November 27th disruptions, the most visually dramatic came from Norway. The Arctic flash, a sudden overexposure that blanked out the Polaris array for nearly 4 full seconds, was at first dismissed as a solar reflection, a saturated frame, just a burst of raw light. But deeper inside the logs, buried in subframe reconstruction and backup metadata, was something else. A circular echo, and it changed everything. Unlike typical overexposure, which floods an entire sensor uniformly, this event had structure. When forensic analysts at the European Centre for Optical Diagnostics ran a layer separation of the corrupted data, they discovered that the saturation wasn't even. There was a clear radial gradient, with higher intensity centred not on the core of 3i Atlas, but offset slightly, by about 1.2 arcseconds, toward an adjacent region of the sky. This offset became important because when the pixel bloom was mapped using cylindrical projection, it revealed a ring. Not an actual object, not something visible to the naked eye, but a recurring halo of brightness within the overexposure, faint, symmetrical, and remarkably circular. This wasn't lens flare. The orientation of the optics, light source angle, and internal lens elements ruled that out immediately. What remained was something far stranger, a light echo, a phenomenon typically only seen in astrophysical events involving extreme brightness bouncing off interstellar dust. Except this wasn't dust, and it wasn't in deep space. It was happening within Earth's observational atmosphere at a distance no farther than mid-orbit. And inside that ring, a shape. It took several days of computational deblooming, but what eventually emerged was a ghost image, a blurred, circular structure at the centre of the flash. Not solid, not clear, but present, and oddly consistent with similar ghost shapes seen in prior imaging attempts from Thailand and Spain. What made this one different was the echo around it. The team referred to it as a circular interference zone, a ring where something had partially disrupted the light transmission itself. The boundary showed a distinct drop in luminous intensity, as though light had passed through a medium with different refractive properties, like the edge of a lens or the contour of a structure. To some, this was enough to theorize the presence of a shielding mechanism, a physical or energetic barrier that not only altered the light we were receiving, but selectively blocked certain frequencies. Others suspected something more intentional, a cloaking interference field, designed not to make the object invisible, but to confuse sensor arrays by mimicking natural light fall-off. Whatever the cause, it wasn't random. The echo's diameter was measurable, its boundary was clean, and its geometry was too perfect to be atmospheric. Worse still, when analysts overlaid the faint circular outline from Norway's flash with previous anomalous frame shapes captured in Thailand's loopback and Spain's missing footage, they discovered a match. All three anomalies, despite different types of failure, had occurred when their systems had glimpsed this same circular zone. It was like a kill switch radius. Get too close to imaging it, and the system shuts down. One astrophysicist from Uppsala compared it to a perimeter tripwire, not a weapon, but a threshold, a border that, once crossed by high-resolution optics, triggers a distortion event strong enough to crash or overwrite the observational channel. That would explain why the object always seemed to rotate away just before cameras failed. But this time, in Norway, something was caught before the system shut down. Something round, at the centre of the ring. Theories range from a natural reflective shell to a gyroscopic stabilization module, or something far more advanced. But no one has yet explained how a light echo could carry such precise radial symmetry without reflecting off a solid surface. Unless, of course, there is a solid surface, and it's just hidden, behind a field we weren't meant to see through. The circular echo wasn't an accident. It was the outline of something still inside the light. At first glance, the systems worked flawlessly. Calar Alto in Spain, Polaris in Norway, and Doi and Thanon in Thailand had each captured their final sets of frames just moments before the blackout. Each system was synchronized with atomic clock-calibrated timestamps, corrected in real time via Network Time Protocol, NTP, links to international GPS satellites. The idea that these highly tuned observatories could be even a fraction of a second out of sync was inconceivable, until someone actually checked. The discovery wasn't made by a lead engineer or a national space agency, but by a data archivist in Oslo tasked with auditing frame headers from Norway's partial backup server. The archivist noticed that one of the Polaris images, frame 6, had a strange discrepancy. Its internal file timestamp and its embedded camera module timestamp were off by 1.3 seconds. That may sound minor, it's not. Observatories that operate on tightly synchronized instruments do not allow for second-scale drift, especially not mid-capture. Every camera module records metadata within the image file: temperature, humidity, orientation, and most critically, timestamp precision down to milliseconds. These are later compared to the central timekeeping system to ensure frame alignment. But this wasn't a minor drift. It was a directional offset, one that appeared only on the final captured frames before the blackout. When similar header-level checks were done on the Spanish and Thai observatory data, the same anomaly appeared. In Spain, the offset was 0.9 seconds, in Thailand, 1.7. But all three shared the same two traits. Only the final 2 frames before blackout showed the drift. The drift occurred in one direction, forward. The system was behaving as if time had stretched ever so slightly. Each frame appeared to capture something that had not yet occurred, according to its own internal clock. This is fundamentally impossible under normal physics, where the camera's capture time should always lag slightly behind processing, not ahead. That's when researchers began looking beyond system error. One theory emerged from a joint paper by a team of engineers at TU Delft and an independent astronomer from Chile. They proposed that the timestamp drift may have been caused not by software failure, but by a temporal distortion in the photon stream itself. In simple terms, the light was arriving out of order. This sounds absurd until you consider that gravity and motion can affect time, a fact proven repeatedly by Einstein's theory of relativity. Under extreme gravitational influence, or in the presence of fields with complex angular momentum, photons can be delayed or accelerated ever so slightly, but there's a catch. For 3 completely separate observatories to observe identical forward-skewed timestamp drift on the same object at the same moment, the distortion would need to be coordinated. That implies an active field, not a passive one. In other words, 3i Atlas, or whatever surrounded it, was not just emitting light, but manipulating how that light arrived at Earth's surface. This becomes even more suspicious when we look at the logs from each observatory's timing server. All 3 experienced micro-jitter corrections in the 30 seconds leading up to the blackout. These are rare events where the time server slightly adjusts itself to maintain GPS lock. Yet all 3 systems, on 3 different continents, had jitter events within a 4.2 second global window. No satellite in orbit could cause that. No geomagnetic event was logged at the time, and there were no solar flares strong enough to interfere with GPS reception. What this suggests is chilling. The systems didn't fail at different times. They failed in a way that made them appear to desynchronize, just enough to fragment the timeline of the blackout. And once that happened, reconstructing the sequence of events became nearly impossible. Because when the clocks lie, the truth disappears with them. Long before the November 27th blackout drew global attention to the 3i Atlas anomaly, something else had already occurred, but it didn't raise alarms at the time. It was subtle, quiet, dismissed as a routine anomaly in system logs. Yet now, with new eyes and context, it stands out like a prelude whispered too softly. On November 6th, exactly 3 weeks before the coordinated sensor failures in Spain, Thailand and Norway, an observatory in Sondre-Strømfjord, Greenland, recorded a brief but precise system-wide synchronization pulse. The event was logged as a 0.0-second resynchronization cycle, meaning the internal timing clocks for multiple instruments adjusted themselves simultaneously, without GPS drift or power interruption. This was rare, but not unprecedented. What made it notable wasn't that the instruments resynced, it was what triggered the resync. At 4:11 UTC, without any visible atmospheric interference, the system clock registered a zero-latency echo from its own outbound telemetry ping. In effect, the observatory sent out a signal that bounced back faster than light normally returns from that distance, as if the space it travelled through had briefly compressed. The data was flagged but dismissed as a software hiccup. At the time, no unusual space weather was reported, no solar activity, no ionospheric turbulence, no satellite maneuvers in the area. It was logged and forgotten. But that same night, 2 other observatories, one in Kagoshima, Japan and another in Chacaltaya, Bolivia, reported identical telemetry phenomena, perfect synchronization events with no apparent cause. In each case, the echo was clean. No packet loss, no delay, and in each case it happened while they were passively tracking a non-priority object slowly entering the outer solar system. That object, of course, was 3I Atlas. At the time, it was still being classified as a hyperbolic interstellar body of interest, with no immediate threat or exotic features. The trajectory was consistent, and no emissions had been detected. But what now becomes clear is that some form of coherence field, may have passed through Earth's observational sphere without being visible at all. These early November synchronization events suggest that 3I Atlas was already interacting with terrestrial instruments, not by crashing them, but by adjusting their perception of time. In other words, soft calibration interference. And this is where things get stranger. When a research team at the University of Vienna revisited global timing logs from the Deep Space Network, DSN, they discovered that several of its relay nodes, including Canberra, Madrid and Goldstone, registered nanosecond-level timing spikes between November 6 and 8. Not enough to disrupt communication, but enough to require automatic correction pulses. These were recorded as minor offset events and went unnoticed, until they compared the timing. All three DSN nodes experienced their offsets within 11 minutes of each other, despite being on separate hemispheres, using different satellites and tracking different targets. What united them was their passive alignment with the incoming trajectory of 3I Atlas. There was no direct ping, no radar emission. The comet hadn't yet passed Mars, and yet its gravitational signature, or something riding along with it, was already affecting the way Earth's most sensitive timing systems behaved. Not with brute force, but with gentle alignment. This phenomenon is now being referred to unofficially as a pre-resonance field, a kind of field or wavefront that precedes the main object, subtly pulling systems into phase, perhaps as a form of mapping, perhaps as calibration, or perhaps something more deliberate. Because here's the terrifying implication. What happened on November 27th, those blackouts, those file wipes, the timestamp drifts, may not have been an attack or a glitch. They may have been the second half of something that began weeks earlier, the response to an earlier synchronization, an echo, one we didn't notice until the silence hit. In the aftermath of the November 27th blackout, most global attention turned to the three affected observatories, Spain, Thailand and Norway. But in the background, another timeline was unfolding far from the public eye, one that included NASA, the Deep Space Network, and a handful of metadata packets someone forgot to erase. It started with a packet capture. At 5:17 UTC, just under 2 hours after the blackouts, an automated tracking system in Canberra, Australia, recorded a telemetry crosslink originating from the Madrid DSN facility. The file header was tagged as routine, a pipeline flush, meant to clear residual data from the previous relay session. These types of transmissions are mundane and typically filled with sensor calibration logs or echo checks. But this one was different. Inside the packet, nested deep within a diagnostic shell, was a string labelled Redirect Pipeline Override XT Channel JPL DSN Node 42. That alone wouldn't be suspicious. What raised eyebrows was the payload it carried. Buried inside the override log was a compressed binary bundle, time-stamped 03:22:11 UTC, mere seconds before the blackout ripple began across Earth-based telescopes. The bundle contained an encrypted image array, along with a snapshot of thermal telemetry and attitude positioning data from an external optical relay node. The source wasn't one of the observatories in Spain, Thailand, or Norway. It was something else, something in low Earth orbit. The thermal map showed clear signs of a controlled pivot, a maneuver that aligned the sensor payload with a precise trajectory vector associated with 3I Atlas. The attitude data indicated a realignment had taken place at 03:21:43 UTC, suggesting that NASA had, minutes before the blackout, already anticipated a shift in the object's profile and reoriented their sensor to catch it. This alone would be interesting, but it wasn't supposed to exist. No public statement from NASA, JPL, or ESA ever acknowledged that a satellite was actively tracking 3I Atlas that night. No orbital telemetry logs listed an event, and no official post-blackout report made reference to any US space assets being involved during the time of the blackout cascade. Yet here it was, thermal data, pointing vectors, and a partial frame checksum, all time-stamped, encrypted, and forwarded through a pipeline labelled override. So how did this escape deletion? A researcher at the Australian Space Research Institute, monitoring open relay packet logs as part of a solar flare latency study, happened to capture the file in a passive buffer. It wasn't labelled as restricted. The encryption on the binary blob was tight, but the header was readable. That was all it took. The file wasn't supposed to be public, but it wasn't classified either. Just buried. What stood out most was the naming convention in the header tag of the payload. MCMVR SW1 Proximity Echo Event Anomaly Frame 0912. This meant nothing at first, but when mapped against known naming patterns used in past NASA mission datasets, it matched legacy tags from Voyager anomaly reporting, used during brief periods when signal delay exceeded expected values or when external proximity events triggered waveform distortion. In plain terms, the object NASA was tracking that night, whether it was 3i Atlas itself or something else nearby, triggered a proximity echo in a sensor originally designed for passive starlight analysis. That alone suggests something crossed the path of that satellite, something that reflected or interfered with its read pattern just before the blackout chain reaction on Earth. And here's the critical part. NASA knew, before the blackout, before the data wipes, before the cameras shut down. They were already watching, and while nearly every trace was scrubbed from public servers, this one forgotten packet, captured not by intention, but by chance, survived. One redirect, one override, one data trail. It wasn't scrubbed fast enough, and now it's the first thread unravelling what really happened that morning. In the days following the November 27th blackout, a quiet ripple spread through encrypted research forums, astrophysics Discord servers, and FTP mirrors used by astronomers to share or capture data. It wasn't a press release. It wasn't a formal discovery. It was a file, a single, uncompressed frame, higher resolution than anything released officially, metadata intact, no watermark, no trace of origin. Its file name was cold and clinical. Orbital Echo Frame 11HAUC. The UC stood for uncompressed. Within hours of being posted, the file was downloaded, mirrored and dissected by researchers in Brazil, Finland, India and South Korea. What they found stunned everyone who had seen only the corrupted or wiped data. The image showed a perfectly clear snapshot of 3i Atlas, taken moments before the blackout cascade began across all three ground stations. But it wasn't the comet that drew attention, it was the background, more specifically, what was emerging behind it. In the far right quadrant of the frame, partially veiled by cometary haze, was a radially symmetric glow, shaped like a disk or flattened spheroid, with a perimeter emission gradient unlike any known optical lensing pattern. It wasn't a star, it wasn't a planet, and it wasn't digital noise. Spectral analysts ran it through phase decomposition models and concluded this glow was not the result of any known camera artifact, and the image's EXIF header told a deeper story. The capture timestamp read 0322.06 UTC, exactly 5 seconds before the Spanish system cut out. The camera ID listed wasn't from any of the known observatories. Instead, it matched a low-orbit US satellite sensor known only by its codename, IRIS-93, originally deployed for spectral studies of atmospheric distortion. In plain English, a military-grade orbital sensor. So how did a restricted military image, full-res, untouched and traceable, end up in the hands of independent scientists? That question became more important than the image itself. Most assumed it was a hack, that someone had breached a NASA or DoD node and pulled the raw file, but the internal signature of the packet didn't align with known hacking methods. There was no brute force, no spoofed credential trail, no malformed server logs. Instead, there was something stranger. The file came from a known academic relay IP, belonging to a university server in Tromsø, Norway. And that narrowed the field. Of all the global observatories affected, only one had direct uplink rights to military polar orbit satellite data, via a shared scientific agreement for studying auroral plasma phenomena. That observatory was Andoya Space Center, and someone inside it, someone with credentials, clearance and access to both civilian and defense data streams, had quietly dumped the file onto a private open-source mirror with no username, no timestamp, and no note. But what finally gave it away wasn't the image, It was the checksum trail. Digital forensics teams traced the original file's CRC hash to a staging server that had previously been used by a doctoral student, one who had temporarily interned at Andoya under a data anonymization grant funded by the European Space Agency. Her name was redacted in every public mention. But researchers began calling her the archivist, someone who had, over weeks, quietly compiled anomalies from all three observatories, timestamp inconsistencies, partial frame residuals, sensor echoes, and had likely witnessed the blackout in real time. She didn't need to say anything, she just released the frame, and in doing so forced the scientific community to acknowledge that what was scrubbed wasn't an error or overload. It was intentional redaction, a deliberate blackout. The leak confirmed that NASA, or at least one of its partner channels, had a full view before the cascade began. And someone inside chose to let that truth surface. Not with a headline, not with a press conference, just a frame, frozen in time. 5 seconds before the world stopped watching, and now everyone's watching again. To understand the blackout of November 27th, we need to go back, not weeks, but just 3 days. On November 24th, the first indication that something strange was happening to 3i Atlas didn't come from an explosion, a fragment event, or a heat signature. It came from its tail. The tail of a comet is often the most revealing part of its anatomy. Composed of ionized gases, volatile debris, and solar interacting particles, it acts like a long exposure sensor, preserving directionality, acceleration, and charge fluctuations over time. Any change in the tail often signals a deeper change in the core. And on the night of November 24th, something changed. At exactly 21:06 UTC, observatories in Arizona, Chile, and La Palma recorded a sharp inversion in the ion tail's curvature. Normally, a comet's ion tail points directly away from the Sun, pushed by solar wind and magnetospheric pressure. But over a 12-minute period, 3i Atlas's tail did something it should not have been able to do. It bent toward the Sun. This tail reversal was not total. It was localized along a segment about 6,200 kilometers in length, drifting laterally across the main tail body like a twisting ribbon of charged particles. High-speed frame stacking revealed a cyclical pulsation pattern, 3 pulses, evenly spaced, moving against the solar wind. At first, analysts suspected a solar wind disruption, or a magnetic reconnection event, both natural explanations. But when data from the Parker Solar Probe was checked, there was no spike in local solar activity, no coronal mass ejection, no flare, no anomalies. Instead, the models showed something else, a localized field distortion. Magnetohydrodynamic simulations confirmed that the tail didn't just bend, it responded. It was as if a moving magnetic field had passed through the tail, altering its charge flow and particle alignment in real time. The motion was precise, deliberate, and most disturbing of all, it repeated itself twice more within the next 45 minutes. The pulses weren't random. Each event showed the same signature, a reversal, followed by a brief compression of the dust tail, and then a return to normal outward flow. Now, here's where it connects to November 27. Each of those tail pulses on November 24th aligns temporally with subtle fluctuations in ground-based telescope calibration data, micro-disruptions in polarization readings, and brief tracking glitches. At the time, these were brushed off as sensor error, but in hindsight they appear to have been directed interference moments, a prelude to what would soon happen globally. Multiple researchers have pointed out that the timing of these tail pulses seems to mirror what would happen if a vessel or structure inside 3i Atlas were repositioning itself, adjusting thrusters, stabilizing orbit, or rotating an internal mechanism that interacts electromagnetically. It's not fantasy. It's based on the pattern. 3 pulses, 3 arcs of tail distortion, 3 simultaneous telemetry disruptions across different continents. This could point to some kind of internal mechanism within 3i Atlas, possibly one not bound to natural outgassing or solar reaction, but rather something structured, gyro-stabilized, plasma-reactive, or even ion engine-like. Which brings us to the blackouts. If the tail behavior on November 24 was the prelude to the blackouts of November 27, then it suggests a build-up phase, a calibration window, where the object aligned itself with Earth sensors, instruments, and possibly even our satellites. The November 24th behaviour wasn't random flare, it was preparation, a warning embedded in particle motion, a test of field influence and signal manipulation, and perhaps the first time 3i Atlas revealed not what it is, but what it's capable of doing. 3 days before the images disappeared, the tale told the truth, and almost no one noticed. When the fragmented data streams from Spain, Thailand and Norway were stitched together, frame by frame, pixel by pixel, researchers hoped to rebuild a clear view of what 3i Atlas was doing just before the synchronized blackout. Instead, they found something that shouldn't exist in any known comet telemetry. It wasn't an emission line, it wasn't a tail, flare, it was an artifact. But not the kind you blame on a camera glitch or transmission drop. It appeared in multiple frames across separate observatories, using different wavelengths and camera models. In fact, it showed up only in the final surviving frames before systems failed, often embedded just deep enough in the exposure stack to be overlooked by a casual scan. When that layer was isolated and enhanced, the result was chilling. It was a shape, a symmetrical geometric construct faintly embedded in the lower third of each frame. Triangular in some captures, hexagonal in others, but always centered, always aligned to the frame's vector origin, and always at the same angle, relative to the tail of 3i Atlas. At first glance, some assumed it was lens flare, a classic internal reflection caused by sudden brightness shifts. But the pattern didn't rotate with the sensor, it didn't drift, and most importantly it was present in both optical and infrared spectrums. Infrared sensors don't capture lens flares, they don't see light artifacts in the same way as optical systems. For the same shape to appear across both spectrums meant one thing: it wasn't light, it was structure. The first to call attention to it was a signal processing technician in Japan who ran a frame through a Fourier transform to isolate non-random pattern emergence. The result showed a repeating spectral signature along the left edge of the object, an oscillating set of values consistent with engineered reflectivity. In simple terms, the object reflected infrared in a way that suggested material composition. Not gas, not dust, not ionized plasma, something solid, something formed. But how could something so structured ride inside or alongside 3i Atlas without being detected earlier? The answer may lie in how it was revealed. Each of the 3 observatories captured their last clean frames within a 5-second window. Each was tracking 3i Atlas at high angular resolution. But more importantly, each had just switched into manual override tracking, allowing higher gain amplification. And that's when the object appeared. In Spain, the frame showed it as a dense triangular shadow embedded near the nucleus of the comet, with faint ridges along the perimeter. In Thailand, it showed up as a central hexagonal blur just behind the leading edge of the coma, surrounded by a ripple gradient. In Norway, it was clearest, a disc-shaped halo, flattened along the vertical axis, casting a soft glow that bent the tail particles around it. Not only was this inconsistent with natural comet morphology, it was symmetrical in ways that comets simply aren't. Real comets are chaotic, tumbling bodies, shedding material in asymmetrical jets. They do not contain shapes with clean, repeating angles, yet this artifact remained stable in all 3 angles. And that's when the speculation began. Was it a satellite caught in the path of 3i Atlas? Was it a reflection of a secondary body? Was it, as some quietly proposed, the core of 3i Atlas itself emerging from its veil? NASA made no comment. ESA issued no statement. The images, when requested through official data channels, were labelled corrupted during transmission. But the local observatories had already seen them. Some had copies, and within days enhanced versions were leaked anonymously. The verdict was clear. This was not a comet behaving badly. This was an object posing as one. And the artifact that emerged from its core? That wasn't noise, that was a signal. A structure hiding in motion, revealed only when our lenses pushed a little too far. And for a moment, just a frame, we saw it. At first glance, the final surviving images from Spain, Thailand and Norway on the morning of November 27 appeared typical of any deep sky capture. Faint glow, streaked stars, a bright core with a flowing tail, standard comet telemetry. But that was only the surface. These weren't just brightness maps, they were part of a new multi-sensor protocol being tested across 3 observatories. a hybrid imaging mode that layered optical intensity, thermal flux, and magnetospheric polarization into a single stack. Each frame captured not only what the eye could see, but what the instruments could feel. And on that morning, those instruments felt something strange. Brightness maps are simple. They record the intensity of visible light emitted or reflected from an object. They're useful for mapping trajectory, density, and general structure. But what these observatories were collecting went far beyond that. Each site had integrated field-coherent sensors, equipment designed to detect shifts in electric and magnetic field orientation, even at low amplitude. That means every pixel in these frames wasn't just light. It was a data point in a complex field environment. Each contour of brightness had a second layer of information: vector direction, plasma behavior, thermal resistance, and even phase lag between emissions. And here's the critical discovery. When the image layers were separated and reconstructed independently, the brightness contours no longer aligned with expected cometry dynamics. Instead, they revealed asymmetrical flow structures inside the tail, pockets of emission that defied solar wind direction, resistive zones that formed geometric boundaries, and, most shockingly, a localized null field behind the core. That null field was more than a dark spot. It was a data vacuum. In normal comet imaging, the tail diffuses light as it expands, creating a smooth fade. But in these frames, there was a perfect drop-off, a wedge-shaped absence of signal that didn't appear in the brightness layer, but became unmistakable in the polarization stack. This implied that something was absorbing or redirecting electromagnetic energy in a non-random, sharply bounded region behind the comet's nucleus. And that's when researchers began to understand what they were looking at. These weren't passive captures. They were environmental fingerprints. By layering brightness with field interference data, analysts could visualize how 3i Atlas was interacting with its surroundings, not just moving through space like a rock on fire, but affecting the space around it, bending field lines, warping polarization symmetry, and in some cases locking adjacent regions into phase coherence. In other words, the object wasn't just visible, it was active. And when these brightness maps were run through magnetotopological reconstruction software, the shapes they generated looked nothing like comet tails. They resembled pressure vectors, like fluid pushing around a hard surface, more like lift than drift, more like design than debris. One visualization from the Norwegian dataset revealed a vortex trail behind the tail, consistent with aerodynamic shaping, not natural ejection. It was subtle, but repeatable, streamlines, as if something inside or surrounding 3i Atlas was sculpting its wake. NASA's public analysis, when asked, dismissed the anomalies as optical stacking distortions. But this explanation fell apart under scrutiny. The distortions occurred only in specific layers, not across the entire frame. Optical distortions affect all wavelengths equally. These did not. Even more suspicious, requests for the raw sensor output files from the 3 observatories were met with silence, redirection, or denial. In one case, the Spanish center claimed the data had been overwritten during system reset, a move researchers called statistically impossible given the timing, but by then, independent labs had already begun reconstructing the layered maps using partial backups, leaked buffers, and raw cache dumps. And the conclusion was clear: these weren't just images. They were multidimensional recordings of an active structured field hiding behind cometry camouflage. They were evidence of interaction, not just observation. What appeared to be light was the least interesting part of the image. In science, silence is rare, especially when it follows a global anomaly, especially when it involves 3 separate observatories on 3 different continents, all experiencing synchronized technical failures while observing the same object in deep space. And yet, in the aftermath of the November 27th blackout, the silence was deafening. At first, there was confusion, then hesitation, then nothing. Spain's Instituto de Astrofísica issued no formal comment. Thailand's National Astronomical Research Institute quietly postponed a scheduled briefing without explanation, and Norway's Andoya Space Centre pulled its data dashboard offline entirely, citing maintenance. None of them directly acknowledged what had happened, despite mounting questions from independent researchers, astronomers, and even amateur sky watchers who had captured strange trailing shadows on their own hardware that night. The silence didn't stop at the observatory level. Emails sent to European Space Agency departments received polite, vague replies. We are currently reviewing the observations. Preliminary data is inconclusive. There is no indication of system-wide anomalies at this time. But behind closed doors, internal logs told a different story. Sensor arrays had recorded sudden telemetry drops. Synchronization scripts had failed across time-standardized channels, including those connected to ESA's deep space relay systems. Redundant backups had corrupted simultaneously, a statistical impossibility under normal circumstances. Still, no agency spoke out. Even NASA, typically open with preliminary comet data, refrained from adding any November 27th captures to their public archives. The only file added that week was a generic orbital trajectory update for 3I Atlas, ironically time-stamped 20 minutes before the blackout began. Then came the quiet retractions. Several research groups who had previously posted brightness maps, trajectory models, and tail simulations of 3I Atlas began quietly pulling those posts down. Links disappeared from public repositories. Archive preprints vanished without revision notes. Blogs and YouTube channels covering the anomaly were either removed or marked private. The pattern was obvious to those watching closely. Pressure was being applied. And the source? Likely a combination of state actors and institutional self-preservation. The reason? Simple. No one wanted to go first. Because acknowledging what happened that morning would mean acknowledging that Earth-based systems, designed, maintained and secured by some of the most advanced research institutions in the world, had failed not by accident, but by interference. And that interference came from the same direction, the same object. 3I Atlas. Silence in science is not always a cover-up. Sometimes it's a pause, an institutional inhale, a moment of calculation. But the length of this silence, the absence of even basic technical transparency, that suggests something deeper. Fear. Not fear of public panic, not fear of aliens, but fear of credibility collapse. Because if even one observatory had admitted that it saw something, an angular flash, a structured reflection, a broadcast emission, then the entire framework of known comet behavior would have to be revised. And along with it, the reputations of every agency that dismissed 3I Atlas as a passive interstellar rock. So instead, they went quiet. And that quiet spread like a shadow across the astrophysical world. Journalists reached out, interviews were cancelled, live telescope feeds began showing older loops instead of real-time data. Even citizen scientists began reporting takedown notices for shared observations, despite no copyright or sensitive content involved. The only noise came from the edges, independent analysts, hobbyists, and small academic labs not bound by international coordination agreements. They were the ones whispering about tail reversal, about polarized lensing, about the artifact, and in response the mainstream kept its lips sealed. The few whispers that did emerge came through leaks, a satellite image, an internal checksum, a metadata glitch that didn't match Earth's timing, each a fragment, each telling the same story, a story no one with a microphone was willing to say aloud. Because if they did, they wouldn't just be talking about a blackout, they'd be admitting something interacted with us. And the silence in that context isn't just avoidance, it's a signal of its own.